Okay. So today, what we will dwell upon basically is, we'll just finish this the bit that we were doing on dielectric, optical constants of dielectrics, and what we will sort of survey. So just one brief recap of those, because we have had like 3 days in between, and I just want to ensure that people are just sort of remembering the perspective. The perspective is very important, right? So let me just share my screen. Can you see? Can you see, right? Yeah, you can see.
Yes, yes.
Yeah. So basically, as I said, the course is essentially designed on the various factors or the various learnings, various sort of knowledge headers that you need to take in order to understand how you can trap a nanoparticle by light, right? So this is the setup again. This is so the so-called optical tweezers, where we have some kind of a laser which passes through. This is a birefringent material, a half-wave plate, which changes the polarization of light, and then we have this, this thing to shape the beam, change the beam diameter, and then all kinds of optics to finally get it to this microscope objective lens, which has a very, very small focal length, which sort of focuses the light into some chamber which has so it's typically filled with water and some mesoscopic particles that are dispersed, and we trap one of those particles. We confine them. So there are many, many optics here. We need to know the, many, many sort of stuff regarding light and its interaction with matter, in the sense that it goes through lenses, it gets reflected, it gets split depending on its polarization. Some goes straight through, some gets reflected, and then again we have some back reflection from this trapped particle, and that also gets. This is like a dichroic mirror. This is another dichroic mirror which transmits certain wavelengths and reflects certain wavelengths, and all of that is something which we need to understand in order to design a robust system that will actually trap particles with like with sort of high efficiency, right? So at the moment, what we have studied till now is how light interacts with this. These are dielectric materials. This can be a metal surface. This is completely a dielectric, which a dielectric which is very, very polarization sensitive. So we've had to study how different polarizations transmit and reflect. What is the ratios of transmittance and reflectance and all that. And of course, at the moment, what we were doing is finding out what happens when we change the frequency of light as it interacts with different dielectric materials. We have covered the Fresnel transmission and reflection ratios and all that. We've also looked at how how metals behave with light, and that is very, very different from how dielectrics uh, uh, and say vacuum uh, interacts with light, in the sense that the when you interact with metals, what happens is the magnetic field becomes much, much higher. There's much more energy stored in the magnetic field, and that is basically because the light cannot really penetrate a metal and dies quickly just after penetrating a very little of its surface. So presently we are just finishing this fact of these aspects of how optical constants, how the various properties of of light, mainly in terms of its velocity, as well as how it is absorbed as it sort of interacts with dielectric materials, as a function of its frequency. So that is where we were sort of we had stopped. And the last class, what we did essentially was, if I just go back, what we did was we stopped at uh, yeah. So essentially, we just wrote down uh, wait, yeah. So basically, we just wrote down the optical constants at different frequency regimes, and what we finally ended with was this, that we saw that there is a real part. So basically, a very important factor that we have studied is the microscopic origin of refractive index, right? So that is how the refractive index is indeed the response of a material when light interacts with it, when light is incident on it, right? So essentially, this is part of linear response theory, where you have some incident light, there is a material, the light yeah, can you hear me, guys?
So you were not audible for last 7 8
Yeah, no,
seconds.
no. Yeah, because we had a power outage and I was
Sir, your
wait.
voice is breaking.
Yeah, so is this recording? It's still recording. Okay. Fortunately, it has immediately put me back, and I don't think I've lost too much. Can you see my screen?
Your screen is fine, but your voice is breaking.
My voice is breaking. In that is again something that I can't. This
No,
is
now
bad.
it's fine, sir.
Now it's fine. Okay. So basically, what we saw in the last class was that there are these the refractive index, the real part of the refractive index, and the real part of the refractive index. We saw how the frequency depends on it. Typically, what happens when the frequency is very close to the resonance frequency or the frequency of the electron. So what we think of here, how we understand the material is that this is like a dielectric material. These are made up of bound electrons. Essentially, I have electrons which are bound to the nucleus, and they can be understood as oscillators. We have the light. We have the light as some kind of a force field, which is nothing but the damp-driven harmonic oscillator. And of course, we know that the damp-driven harmonic oscillator solution has a real part and an imaginary part. So the real part, again, the solution. So essentially, the solution is nothing but what we get. We relate to the refractive index in a certain manner using immediate constants. The real part of the refractive index deals with propagation, and the imaginary part deals with absorbance. What we saw very interestingly is that and so the how they behave. Let us just quickly see the behavior. Right. So essentially, this is the the imaginary part, the K, and this is the real part. And as you see that in this regime, so this is the resonance frequency omega zero, where at the resonance frequency we see that this is n minus one we plot. So n minus one essentially is zero, and the absorptance or the I shouldn't say absorptance. Yeah. So maybe this is the this K is something that leads to absorptance. It's the absorption coefficient, and that is maximum at resonance. This is very interesting in the sense that this is actually like almost like a straight. So this graph, by the way, this is a classic dispersion sort of a graph, and you will find this in many other branches of physics, especially in active feedback circuits. So, for example, what is an active feedback circuit? So, suppose you have some kind of a, say, some little, some metal block or something whose temperature I want you to control. Okay, and therefore you need to. So, what I mean temperature I want to control is that suppose I say that it's 25 degrees centigrade. I want you to keep the block at 25 degrees centigrade, right? So then you have to design some kind of a system where the temperature is measured. If the temperature changes, then we give some kind of an error signal. So we have an active heating or a cooling element, heating and a cooling element rather, which will control the temperature. And we need to give some kind of active feedback to that element, which will tell it to heat or cool. So in that kind of a feedback circuit, you get exactly this sort of a response for what we call the error signal. And those who are interested or who will want to take up things like atomic spectroscopy for your term paper, you will actually see that this is exactly the type of signal you will encounter when you actually will like to say fix the frequency of a laser to an atomic absorption peak. It will exactly look like this. So this is also how the refractive index varies with frequency, the n minus 1. And interestingly, the properties near resonance are the really fascinating things. And as we noted here, what we noted was that as when you in this regime, this is like normal dispersion where as you increase omega, n also increases. This part is not normal. This is anomalous dispersion, where as you increase omega, you have n decreasing. And this part again is sort of the same as this because you increase omega, again your n is increasing. However, at infinity omega, you will again have this n minus 1, which will reach at 0. What is interesting, however, is this region where we have very interesting properties where we actually, by the way, we also saw last class that in spite of what you will feel intuitively that at resonance the absorptance will be high. That is not the case. Even though the absorption coefficient is high, we saw that actually reflectance is very high at resonance, basically because the reflectance is given by the Fresnel formulae. And we saw that because n minus 1 is 0 at the resonance, it essentially tends to like close to 1, which is actually what explains the color of material. So at when you sort of shine light at a particular color and there is some kind of a resonance, then the material, for example, if you have a dye which absorbs that red and you shine red light on it, then the whole the dye will appear very much red because it will actually reflect that color more. It will not transmit anything, and the rest of the colors may be absorbed much more. So that typically what you will find, I mean, the color of objects when you actually shine light that is resonant to it will always appear as the color of the light itself, right? So that is what one might define to be the color of objects. So what we will do now is to look at so as a consequence of this, this sort of phenomena where near omega 0, you have the anomalous dispersion. You can well understand that when n minus 1 is in this region, when it is actually less than 0, then n will be less than 1, which means that the phase velocity, which is given by c by n, will exceed the velocity of light. So what we will try to understand today is how that can be explained physically. Okay, so that is what we will start with today. And then we will go on to actually explaining a real sort of a dielectric material, some kind of ionic crystal, as they say. I will just explain it how the dielectric constant. So essentially, you will remember that refractive index comes from the dielectric constant, that is epsilon. It's just root of epsilon. So if you understand the behavior of epsilon, you know the refractive index as well. So I will just treat you to how epsilon is written for these ionic crystals, and I will leave you with an assignment where you need to find out the reflectivity of a certain material over I think it's magnesium oxide, which we will actually you will I will ask you to find out the optical constants from literature and then plot the reflectance against omega and really figure out how these things work. Okay, so essentially what we will start with today is the explanation of phase velocity greater than c. So this is like the physical physical explanation. Okay, so this part is very nicely treated in this book called Bohren and Huffman. So we will deal mostly with that. Please have a look at this. This is a very interesting book, especially for scattering phenomena. This is an excellent book for plasmonic scattering. This is really, really very good as a book. Okay, so what we have, of course, is that your VP is omega by k, and that is some c by n1, which means that if n1 is less than 1, then your c is sorry, then your VP is greater than c. So Acha, here we will assume something, so that I will request you to sort of, believe me in some certain one expression I'll write, which I'll ask you to believe. However, the derivation is done in this. Just the scattering part, we will sort of the expression for scattering, we will assume. So essentially, so this is something which we discussed the last class. Okay. So what we had a long discussion. I think Anirudh or somebody asked. So what we was trying to say, yeah, I think Hitesh asked, right, that I was trying to give you this thing of how quantum mechanics, how we can make a quantum picture out of this, and we can try to say that when you actually have the absorption maximum at resonance, that essentially means that the electron really absorbs light, all the light from the excitation, and it goes to a upper level, and since it cannot stay at that level, it has to go down to the minimum energy state, and therefore it sort of scatters light, and therefore you have like the reflectance. You can try to argue with that in that sort of manner. So that is basically also some kind of assumption that we will make here, in the sense of not the quantum picture, but but what we want to say is that the passage of light through a dielectric, through any dielectric, so is nothing but the excitation and subsequent emission, which is a radiative process, radiation of dipoles, right? So what I'm going to say is that the electric fields, if I say the electric, since it has to be, we have to have conservation of the field. So essentially, the transmitted one field is nothing but the incident field and the scattered field. This is very important. So I'm saying that the transmitted field is nothing but the incident field and the scattered field. And here, as I think I told Anirudh the last class, is that what we find is that the scattered field, this is zero for all directions other than the sort of forward direction forward direction, where forward direction. So essentially what I'm trying to say here is that, so these are waves. First of all, remember, this is a wave, this is a wave, this is a wave. So essentially the scattering, so that one thing maybe you know. So have you done actually dipole scattering somewhat? Have you studied dipole scattering anywhere? Guys, have you studied in your EM theory somewhere?
No, sir.
Dipole radiation? Dipole radiation if not studied, is it?
No.
Oh, dipole radiation was supposed to be covered. Okay, it's there. It was there in your syllabus, right? So I
Yeah.
will really, so please study this. Please study this. So please, this is very important. So dipole radiation, please refer Jackson, Griffith also is quite good. Or yeah, these two books are extremely good. Please have a look at this. Okay, so essentially when you study dipole radiation, you'll see that the maximum happens in the forward direction. Okay, so what therefore it means is that uh, other, so what happens if you now ask me what I mean intuitively, I mean obviously the expression tells you that this is how things happen, but what you can also understand, what sort of here what we can argue is that because these are waves, in other directions you basically have destructive interference. Okay, so all other directions the amplitudes basically cancel out, and what you have is a net propagation in the forward direction. Net sort of, the field is maximized in the forward direction, right?
Uh, Sir, how did
Yeah.
you add ES to EI to get ET? Even so that
How?
the
So
how did the
yes,
incident increase?
incident. Sorry, how do the incident?
How is the transmitted greater than the incidence?
No, no. So this is a vector thing, right? So okay, so that we will show. So this is actually a vector diagram. So this is not like just a thing. It's not a addition of parts. I mean, this is just a vectorial thing.
Sir,
Okay.
is
Okay, this is a
ET E
vectorial
total
thing.
or transmitted?
Transmitted. Okay. So in the sense that this is the one that goes through actually. So this is a vectorial thing I had that we, so when we, so I will just show you the picture. When I show you the picture, it will get clearer. So it is a vectorial addition of that. So these are like in terms of direction I'm showing, not so much like actual amplitude sum. Okay, so obviously it cannot be like, yeah. So this is a vectorial thing. So there is, so what you will, so what I try to show here is that there is some kind of a field which is coming in. Not all of it is scattered. Okay, some of it goes unscattered. So this is, so what you can say is that this is like the DC part. This is the DC part, and this is like the signal part. Okay, so there is an offset in the sense that that is the part that is unscattered, and this part is the scattered part. And so in terms of, if you want to know in terms of magnitude, okay, in terms of vectorially, we'll just in the diagram that we have that I'll show you then. So it's like basically sort of a vector diagram that we have. And essentially it is, the crucial thing is in terms of direction, we have the forward direction, only the forward direction where this ET is actually there. Other, I mean, exists in other parts. What we have is that the ES sort of is zero. It is it. So what actually has is, so in other directions, what you can say, you have constructive interference happening in this as well. Okay, this is the only direction in the forward direction where you have constructive interference happening. The other parts you do not have sort of transmitted light. In the forward direction is where you have the maximum transmitted light, because in the other directions you essentially have so actually what one should write is that this ET is zero for all directions other than the forward directions, where your ES interferes constructively with EI. Okay, so this is actually the crucial part. So I should basically, maybe this arrow is a bit misleading, so I should not put this arrow here. Okay, so basically what I want to say is that this part is the crucial, the transmitted part essentially is highest in the forward direction where you have constructive interference. Other parts, this and this sort of destructively interfere, so that finally you do not have any transmitted light. So now there is one sort of assumption that I'm going to make, and this part is, the math is sort of done in Boden and Huffman. So what I'm going to assume is that for this dipole at 0 degree, if I take the scattering angle to be 0 degree, then this ES is sort of proportional to, this is an assumption, okay? Okay, where this, okay, so this alpha.
So this is IK cube, right? What did you say?
Yeah, of course. Sorry. Yes. Sorry. I just wrote it. Yeah. This IQQ. Yes. So this part, so this is, this formula is derived in detail in Boden and Huffman. I will ask you to refer this to this book. Essentially, what we sort of write down here is that I don't know whether we can try to explain this. So this is essentially your polarizability. Okay, this alpha. This alpha is nothing but the polarizability. Okay, this is the polarizability. So what? Let me see if I can just try to understand this. So essentially, what we are trying to say is that, oh, 1 minute. Yeah. So essentially, what we are trying to say is that this cube is, so this is a classic scattering for you guys. Have you guys looked at scattering in quantum mechanics as well? You've not looked at, no? I mean, that also is probably a bit advanced. How this K cube sort of comes.
No, they should have. If ADG taught, he should have taught the.
Yeah, so if you have studied classic the bond scattering approximation, then this is something which is fine there. Did you actually study, or are you actually studying now?
It was in the course, but obviously online course made it impossible to cover.
Oh. So I don't know. I mean, Bishwajit, can we kind of argue why this K cube should be there? Because see, the derivation I don't want to do here, but I don't know. Can we argue somewhere where this thing is? I can't.
I can't think now.
Yeah, it is to argue why there should be K cube, in the sense that, see, so this is essentially, see, this is a classic scattering formula. Okay, so when we actually do scalar diffraction theory, so then also we sort of have a thing of that sort. This is again for classic dipole scattering. This is how the formula comes. So I think if you, I mean, see, for me, it is, I cannot physically argue why this should be there. But of course, if you again look at the dimensionally and all that, then you'll see that this will be fine. But if so, this is Of course, this is not directly derived in Bohr-Huffman also. I think you have to look at classical scattering theory to argue this. But I see, but the important part that I can tell you is that even if we assume this, the phase velocity part, that does, in order to understand, how that is greater than c, or how we sort of justify that, that will not depend on this. This much I can assure you. So if you can at least agree, I mean, just sort of take it from me that this goes as this. Then the rest of the part, we can argue whatever, we can.
But sir, in Bohr-Huffman, the derivation is actually done. Basically, you
It
can
is
see
actually
that.
done.
Yeah, for dipole, it's basically you'll see that the Bessel, if you expand the Bessel function, the lowest order term will be in x cube. So there you can
Okay.
get the AK cube.
Okay, so I think it is done there. So no better, yeah. So okay, so I think Jibon, it is done in one of the earlier chapters, no, not in the this chapter. It's probably done in the very earlier chapters which
No,
deal
chapter
with
5,
scattering.
chapter 5.
Chapter 5 is probably okay.
Yeah.
So please look at this. Is I will again write down. So Bohren and Huffman. So maybe I will put this as an assignment. Chapter 5, this one. So we will put that. So please look at. I will put this as an assignment. So everybody has to learn this. So anyway, so what we will. So is now what we can write this one, because this is again an imaginary thing, right? It's polarizability, so it obviously has a real and has a real and an imaginary part. So what I can write as this is something like this. Okay. So this theta, this is nothing but the phase between the scattered and the incident light. This is the crucial part. This is basically the response. Okay, so you can appreciate that the whole thing depends on this. The whole argument that we have will essentially depend on this. Okay, so this is the phase that we have finally between, so the response of the electron is represented by this phase. Okay, so the argument goes as this, that basically, so okay, so then we have like the several okay, see, right, so let me just write this down in a better way. So essentially that means I can write this as some yes is some k cube alpha e to the I theta minus pi by 2. This is fine. What I'm writing is this I am writing as this. There's a minus. Okay, this is fine, right? Theta minus pi by 2. This is fine, right? So then I will basically consider two domains, omega less than omega 0 and omega greater omega 0, right? These two domains are what is interesting. This is fine, right? This is just I have written minus I wrote like this. Right?
And said that alpha equals to that value into e to the power I theta, right? Not I
yeah,
k
yeah,
theta.
yeah, yeah.
I there is a k.
Right. Oh, sorry. Oof. I'm just horrible. Obviously, I theta. Yes. Okay. So.
Sir, and the denominator in ES?
1 minute. What?
The denominator, like the 4h cross.
4 h cross नहीं 4 pi. Oh, वो h cross नहीं है.
Pi. Sorry.
That is pi. sorry. It is pi. It is not quantum, yaar. There is no question of any h cross. But this is handwriting cross. Okay. So then what did we have? Let me just write that again. So ES was some k cube alpha e to the Oh yeah, that pi. We can write that. Whether you keep it or not, it's like proportional, right? So alpha I theta minus pi by 2. So very obviously, and now how does this go? Now let us. So you understand. So what
4
should
pi,
we
I
take
think so.
recourse to? Huh?
It's 4 pi, right, in the denominator.
4 pi. Right. So what should we now take recourse to? I now want to think of how this changes with. This is how the response changes with omega. So which diagram should I think of? Huh? This is the one, right? 0 pi. This one, right? Right? This is the resonance curve of phase versus omega, right? Anna, what? Yes or no? Omega less than omega 0? Theta tends to what? Right or wrong? क्या बोलो boss? This is correct, no? Arey, complete stunt. Can you hear me? Oh God.
Yes, it is
Hello?
clear.
Okay, very
Why?
good. Yeah. So because unless you respond, I don't know if I'm there. So then this becomes, if I look at the total, so this is nothing but e minus pi by 2, right? So I can write my et as some e0 e to the I omega t minus pi by 2, right? Because it's this is just a thing, it's is essentially es plus et, which basically means that my et lags my ei, right? Because ei is essentially this one, right? So this is out of phase very clearly, and that basically implies that my phase velocity is slower than c. And obviously what will happen for the other thing, that is when you actually have omega greater than omega 0, theta what tends to pi, right? Which means your et will be e0 e to the I omega t plus pi by 2, right? Which clearly says that et leads ei, which essentially means that phase velocity is greater than c. And now I will this is very nicely illustrated in this picture that I am directly taking from our friends Boren and Huffman. So can you see this clearly? So this is essentially, this is my omega less than omega 0, and this is my omega greater than omega 0. And Rohan, this is essentially what I'm trying to say. So I have this ei, es, and this is a vector diagram. So very clearly you have v less than c, and this is what they show. So you have essentially your this dotted line is the transmitted, this is your incident, I is the incident, and this is your scattered. Okay, so you can see that in this case you have the dotted line, which is the transmitted, that is actually lagging the incident field, whereas in this case the scattered field is, because of this what we had, it is essentially leading my transmitted field, which is nothing but, saying, which is saying nothing but, this case, you actually can have the phase velocity greater than that of the velocity of light. But again, very important, does this violate STR? And certainly no. Why? Because since STR cares about signals propagating at V less than C. So what does this mean? So for example, so please understand. So STR essentially tells you that, let me write this less. So STR basically says that you have an observer, you have who has maybe a detector, and there is maybe so you say Bob and Alice. So Bob has a torchlight and has a detector. Bob switches on the torch. Alice essentially measures the time it takes for a photon, or for takes so just measures the time it takes the signal to reach her. That is what should be less than C, and that is absolutely not violated. Because remember, what we are dealing with here is that you have an interface, you have light coming in from one refractive index into the other, and then what is happening is that the envelope, so the in the phases, which comprise the wave, those are the disturbances or whatever you say, those seem to be progressing at a velocity which is different from C, which is at times even more than C. That is absolutely not saying that any signal will propagate at any velocities which can exceed C. That is very different from this. Okay, so there have been a lot of interesting experiments which have been done in order to demonstrate this slow light, and so at times you can also have light slowed down enormously. Okay, you can have situations where, so you basically have both slow light as well as fast light, or whatever, fast light. So this will be like V much less than C, and V much greater than C. So I will certainly say that I think some of you should talk about these things. These have been experimentally demonstrated very beautifully on all kinds of interesting materials. So this will make very nice presentations for your term paper, both how this has been done and what this means. Okay, that will really lead to some nice learning. Okay, so this is basically, this is the argument that is presented in order to justify why light can actually move faster, than, wave can move faster than light because of certain frequencies of incidence of the light. After this, so any questions here?
Sir, I couldn't understand why ET leads EI in phase should imply that the phase velocity is greater than
So
C.
basically what it means is that, what this is meaning is that, if you just think of this, it basically is meaning that here, so if you think of this, both are starting from, say, a location here, and what is happening is that T is actually traversing the same distance in quicker time, right? So this will arrive before the incident rate, right? And suppose you think that the distance traversed is the same in the material. If this arrives earlier than the incident pulse, that means that incident wave, sorry, I shouldn't say pulse, incident wave, okay, they are traversing the same distance, then that essentially means that this is traveling at faster than C. So I am assuming that the distance is the same. Suppose this is your, this is the incident and the scattered wave both are emanating from this point, this level. Okay, and then what I say is, I then have some, I basically note when this will come here, and when this dotted line comes and when this comes. So I will essentially see that this actually is leading in phase when it will actually arrive faster. I will arrive before the incident line, which essentially means that since both have started from the same point, one is actually coming before the other, which means that it has traversed the same distance faster. Whereas in this case, it is the opposite. It is arriving later, which means that it has velocity is slower than that of the incident wave.
Sir, but the dotted wave which is there, that also starts earlier, right? Like starts later. I mean,
No. I'm
later
saying
and
that
reaches.
when it is emanating, right? I'm assuming that this is the electron. Okay,
Yeah,
both of them. This point you have all three, right?
yeah.
You have all three, so they are
Right.
all starting from the same thing, right? And then so
Okay.
phase is nothing but in time you have, right? That is nothing. The amplitude is basically you can draw in terms of phase, no? I mean, sorry, the
Right.
time. So that is meaning that this is coming earlier in time, right?
Okay, sir.
Okay, so
Understood.
then when I understand, I just measure. So actually, in the experiments that they do, this is exactly what they also look at. Exactly what they also look at. They see that one of the pulses so they do it with pulse lasers. So they see incident pulse and then the pulse through a medium, and then they sort of calculate that the pulse seems to have appeared earlier than this incident pulse. So they conclude that it must have traveled faster than light. I mean, inside that thing. But if the moment you want to put any information out, that information will still take less of them thing. Here you're not there, you will not care with any information. That is just some, in the experiments that they do, that is some inference. They infer that you actually have the pulse must have traveled faster than light in the medium. Okay.
Okay, sir. Thank you.
Okay. So let us move on. So now what we will sort of end this chapter off with is essentially look at ionic crystals. So this is the last part of this. Is very interesting. So here you essentially have uh, some crystal which has, of course, the atoms arranged in lattice. So there are two modes of vibrations. Okay, so there is this lattice. So obviously there is the electron vibrations, of course, and there is also the lattice vibrations, and other vibrational modes of crystals. Okay, so when I say other vibrational modes, I basically mean there are also molecules, right? So these molecules also have their own vibrational modes. Now, so that I think I'm sure you guys have heard of, right? You have in molecules you have rotational energy levels, vibrational energy levels, rotovibrational modes. So the important aspect about this is that these are all separated out in frequency. Okay, these are all separated out in frequency, and what we generally assume is that uh, because you have different regimes. So what we typically say is that in the low frequency regime, we have the effect of the effect of the electrons. Finally, at the low frequency regime, we can just take from whatever we did just now, right? We had when we wrote down the formula for the dielectric constant, we had two regimes, right? We had a low frequency regime and we had the high frequency, the intermediate regime, and then the high frequency regime. And what we saw was that in the low frequency regime, the electrons, essentially the vibration, the epsilon, sorry, the dielectric constant, that is epsilon, yeah, that was independent of frequency. Okay, that is very important. Okay, so what we write typically is that part where we have in the low frequency regime, we write down sort of, the electronic contribution at this very low frequency where we do not have contribution of other things, the lattice and the molecular, so remember, the molecular vibrations and all that basically mean that they are doing some transition from one level to the other. Okay, so that is essentially that is what decides the molecular vibration, and the lattice also, it is the vibrations happen in the form of phonons and other interesting things. But the way to approach this is that the lattice and the molecular vibrational modes are, this is very crucial, are well separated from the electronic vibrations. This is very, very important, since the frequency is much lower for the latter. This is also important, right? Because there you just have the electron itself generally just vibrating, whereas when you have transition between two molecules and all, between two molecular levels or atomic levels and all, those are typically much higher frequency than just the frequency needed for the, then the frequency we are looking when the electron is not going through a jump, it is just vibrating itself. Okay, so that is so just understand what we are saying. We are coming with some incident light that has some frequency, and so if the frequency is not enough to affect transitions between molecular levels or atomic levels or lattice phonon, energy levels, phonon energy levels, then that energy is not, that frequency or the energy that the input light comes from, that is not completely wasted. That is still there in order to just vibrate the electrons. So the energy is not enough for the electrons to leave the energy levels that they have. So can you appreciate this? The why I am saying that the electronic vibration levels are lesser than the lattice and molecular vibrational modes. Is that part clear? That part. So what I'm saying is that if the energy, the moment I increase the frequency or the energy, the electron will actually leave its level and go to higher levels. Whereas when I'm having low frequency, then it is just electron itself is just sort of jiggling around. The jiggling around is increasing. The amplitude of the jiggling is increasing. But when I actually increase the frequency, then it will go to higher energy levels itself. So obviously the electronic vibration modes, those are much lower in the threshold for energy for them is much lower than what you need for the lattice vibration and the molecular vibrations. In order, that you need to trigger the lattice vibration or the molecular vibration modes, right? So then what we, yeah, right, yeah.
The electronic energy levels are quantized, right?
Again, electronic energy levels are quantized. Yeah, you can say that. Yes, you can say that. But again, remember, Rohan, when I'm saying, when you talk about electronic energy levels, that essentially, yeah, that means that you are still giving the energy. There is a difference between two energy levels. Okay. Whereas what I am saying here is if I don't give that level. So of course, in quantum mechanics, what you kind of causes an increase in the overall temperature of the bath. Okay, if I just think of that, I can say that this is some kind of, half mv square equal to kbt or something. My temperature, effective temperature increases, but nothing happens to the occupation level. I mean, the electrons jumping from their level to the other. In classical, if I look at the wave picture, there is no problem, absolutely no problem, because I'm just saying that this is not enough for the electrons to actually, if I electrons to uh, initiate any sort of lattice vibration or initiate any kind of molecular vibration in the crystal. It is much lower than that. So the electrons essentially, but for classically, you can understand that the electrons themselves are the vibration or the amplitude of the electron vibration that is increasing. In terms of quantum mechanics, I can say that I am not giving enough temperature, energy for the electrons from going from one level to the other. But I am probably increasing the effective temperature, in the sense that I can still say that there is the probability density or something, so that becomes wider. If I plot that thing becomes wider. So they have greater probability of being found in different, slightly away from their eigen levels or whatever, something. If I have a spread, I'm thinking if I do a measurement, there's a spread, that spread sort of increases. Classically, there is no problem. I'm just saying that I'm giving very low energy, so the electrons are vibrating, but I'm not giving enough energy to basically induce other sort of higher energy transitions.
So you're saying that between two electronic levels there are multiple vibrational levels. So the
Yes, that
electrons
also
actually.
absolutely. There are multiple vibration levels. Yes, okay. In a completely quantum picture, you can think of that stuff. In fact, typically atomic levels are much more wider separated than molecular levels. Are far more separated. Typically, molecular spectroscopy needs much, lower wavelength light than atomic spectroscopy. So that also is a way of, if you want to completely understand by the quantum mechanic picture, that may not be too bad. Okay.
Okay.
So in the sense, but then basically what I'm trying to say is that I can, in writing my expression for dielectric constant, I can separate out two regimes. Okay. So what I'm saying is the low frequency regime, essentially, the effect on electrons can be taken from the low frequency limit of this epsilon. Okay. So remember, so when I say epsilon, this is imaginary part. So by the way, so what does this imply? What was the imaginary part at low frequency limit? That went for what? Epsilon R2. What was the expression? You remember? It was going as what? What? Forgotten completely.
Omega p square gamma upon omega into
Yes.
omega square is gamma.
Gamma. What did I write? P square gamma omega by omega 04, right? So that goes to 0 because this tends to 0, right? Which means that epsilon is real, right? That essentially means that so this is when omega less than omega 0. So that means I can write my epsilon as some epsilon naught electron contribution plus, then I have some difference, I'll tell you. So this is omega pi by omega t square minus omega square minus I omega gamma. Okay, so this So what is this? So what we have is this guy is nothing but the electronic contribution or at low frequencies. Okay, and so this omega t that we wrote here, that omega t is this is typically called the transverse optical mode in ionic crystals. This is the resonance frequency. This is just this is what. So basically, this is something that can be, and the word transverse comes because it can be excited by photons. That is why this transverse thing comes. It's like a resonance frequency, but this omega p square, that is the that is again like a plasma, you know, the plasma frequency. But now what is important is that this definition is now given by mi, the mass is replaced by mass of ion. Okay, and this is like mi is the mass of ions, and this is obviously much lesser. This is about 1,000 times smaller than me, which basically implies that omega p I is much less than omega pe. For the ionic, the plasmonic frequency, that is much smaller than the electron plasma frequency. Okay, so we will quickly just summarize what happens here. There's nothing great that is resulting, but the interesting part is at the point where omega equals omega p. That is really fascinating. Let me just write down, summarize these. So consequences will be just that you have normal dispersion around each. I'll leave you with a question and of course an assignment. Around each side of omega t, that is fine. Then you have anomalous dispersion in a narrow region around omega t. This is absolutely fine. High reflectivity in close vicinity of omega, where typically omega tends greater than omega t around, and also add that. And that is very clear because n tends to 0 and k is large. And the last question that the last statement I leave as a question. What happens no, so let me just write down, yeah. So what happens at, okay, so let me just write down this guy first. Let me just write down this guy first. So what did we have? We have epsilon r1, right? So for high frequency, okay, so let me see that. So at high frequency, you have, like, so for example, if omega p has much greater than omega, and for yeah, omega much greater than omega t. Okay, suppose these are two conditions. So we have epsilon r1 equals to epsilon 0e minus omega p square by omega square. This is fine, right? I'm basically saying that this plasmon, this has to be I, because this is much greater than your omega, and this is much greater than this. So I can basically write this. Okay. Now you can sort of appreciate that I can have a condition where epsilon r1 is 0, right? When basically these two match, right? So what happens then? What happens then? What is the consequence? If I basically say that I have this plasma frequency like this, and at very high frequencies, I can write down the real part of the dielectric constant in this manner, and I can get, we can have this, right? What is the consequence? What is the consequence of this fact, this epsilon becoming 0? Any ideas? Can you appreciate what I wrote? Huh?
The speed of light will get affected. I don't know.
Much more interesting thing, Anirudh. Much more interesting thing. We will discuss. I will not discuss immediately, but you think of it. Okay, you think of. No, I will not give you any hint. But think of it. Speed of light, of course. All that will. Some other thing. I in the one of the earlier classes. But why? What is happening? It has much deeper consequence. Okay, this is basically to do with the direction of of light. Yeah, it's very interesting. Very. And the task that I want you to do, the task assignment or whatever task, one will be, of course, that proving that IKQ. The task will be reflectivity of MgO. And I will maybe show you what reflectivity of MgO. This is a known ionic crystal, and you will find out the optical constants from a reference, which is, I will also just write down the reference. So this is, you can do it for different, I don't know, maybe you can do it as a function of incident energy or frequency. I will say maybe incident frequency is better. Relative energy as a function of incident omega. Okay. And optical constants from, there is this paper called Roessler and Walker, 1967. Roessler and Walker, 1967. So this is literature search. You need to get introduced to this. Literature search, you have to search the internet for this, and you will be able to download it. You will get all the values of N and K, and I think it is necessary that you do it in order for yourself, for you to understand how things are going on. Okay, so you will basically get a plot of reflectance, some kind of reflectance versus omega. You will basically get something like this, something like that. Some fixed, of course there is no gap. I just go on changing in, so it will, I can tell you that it varies hugely, and it will sort of vary from maybe, from at least from like 10%. It's not very high. This is like a crystal, okay? It's a dielectric material. That's why it's not that really high. But it will change from like about 7% to even like 2%. And it can go up to like even 30%, 32% at some frequencies. Okay. Is that clear what I'm trying to get you to do? What the task is? Rosler, and so this is again, this graph is given, I mean, the answer is plotted in Borer and Huffman if you want to check, but that is again, they don't tell you how to get it. If you just want the answer, it's there, but of course, you cannot take a scan of that and put it. That will be too easily caught as well. So what I'm trying to ask you is to get a feel of these things, to really understand what actually, when we did all this theory, right? But when you actually do the I mean, when you actually see a material, how this gets translated. So you need to find out, do a bit of digging, find out this paper, and I request all of you to search on your own, because don't ask, just ask Anirudh or Rohan or whoever, Pritesh, okay, Mila tere ko paper bhej de. Not a good idea. Search on Google, you'll get it very easily, and just get N and K, and you have then plot. And I don't know, then maybe intricacies. I can't say what intricacies you might face, but that is the challenge. Okay, any questions? Acha, and you have to tell me tomorrow, you have to tell me again, when I said that epsilon tends to 0, I mean, that thing, epsilon real part becoming 0, what that means. Epsilon real part becoming 0. Okay, you have to just think deeply and tell us what that means, that, epsilon tends to 0. What are the implications in terms of the field? Very, very interesting. Okay. Okay. So we'll meet tomorrow. And tomorrow we'll do root model after this.
Sir.
Okay. Yeah. Okay, guys. So I'm stopping recording. So please leave.